To run today's artificial intelligence models, data centers rely on monolithic server racks like Nvidia Blackwell, designed to transfer data across thousands of processors simultaneously. This enterprise architecture shares its technical lineage with consumer desktop hardware from the late 1990s. Early PC enthusiasts linked separate graphics cards together using a physical bridge. It was a crude connection, limited by low bandwidth compared to modern standards. Consumer multi-GPU hardware is no longer manufactured. However, the engineering required to synchronize separate chips provided the technical groundwork for modern supercomputing. The concept originated with 3DFX and their Scan-Line Interleave technology. It was a hardware solution that divided the rendering workload to increase frame rates. During the peak of the 1990s computing boom, this technology drove a competitive market of enthusiasts and hardware vendors. Strategic errors eventually crippled 3DFX. By acquiring their own manufacturing arm, they alienated major board partners, leading to a rapid loss of capital. Following the 3DFX bankruptcy in 2000, Nvidia absorbed the company's assets, patents, and engineers for $120 million. Nvidia acquired its competitor and the flawed promise that doubling physical hardware would linearly double rendering performance. Alternate frame rendering works by assigning even and odd frames to separate graphics processors. But because 3D scenes vary in complexity, one GPU often finishes its task faster than the other. This results in uneven gaps on the delivery line. To compensate, the system must buffer these frames, which increases input-to-photon latency. This creates a physical delay between a user's action and the visual response on screen. Traditional benchmark tools only tracked average frame rates. They failed to account for these delivery fluctuations, masking the poor user experience. Gamers paid double the hardware cost for high benchmark scores, but the resulting microstuttering made the actual experience feel less responsive than a single-chip system. Early game engines rendered every frame in isolation. Since each image was a self-contained task, separate GPUs could work independently without communication bottlenecks. Modern rendering changed this through temporal data. The current frame now requires data from the previous frame. Because this historical data is stored on a separate card, the pipeline stalls waiting for data to cross the interconnect bridge. When software began to require this constant data exchange, consumer interconnects reached a bandwidth limit. This temporal dependency wall effectively ended the era of multi-GPU gaming. To bypass the limits of consumer hardware, Nvidia transitioned multi-GPU development into the enterprise sector. They developed NVLink, a high-speed, unified memory fabric designed for bandwidth levels that standard consumer motherboards cannot achieve. This bandwidth allows the system to pool memory together, merging separate physical GPUs into a single logical processor. Managing these interconnect bottlenecks requires the precise application of computer science and semiconductor physics. You can study the engineering principles behind parallel computing and data transfer for the interactive courses at sponsor name. The high-precision environments where modern AI hardware is built represent a massive shift from the unrefined hardware of the 1990s. However, the struggle to synchronize gaming chips provided the specific engineering data needed to build today's large-scale AI networks. Today's massive trillion-parameter AI models rely entirely on interconnect solutions that were originally developed to address microstuttering in consumer desktop hardware. This rack-scale architecture established the hardware foundation for Nvidia's enterprise monopoly. We'll examine how they weaponized silicon to control the market in the next video.